This is Idaho sagebrush country, very ordinary to the eye, yet a land of exotic names. The Lost River country, east of the craters of the moon, the Snake, a land of paradox and contradiction, tied to the past by the lava flows of 1,000,000 years ago, yet tied to the future by the work that goes on now. The beaver trappers, the mountain men, came through here over a century ago, learning the rivers and passes, making the maps of memory that enabled them to guide such Johnny-come-latelys as Fremont, and later on, the wagon trains of pioneers who went that-a-way en route to Oregon and California. Those pioneers saw little reason to linger here. But that was yesterday. Today, 500,000 acres of this arid land have become the Atomic Energy Commission's National Reactor Testing Station, commonly referred to as NRTS. Part of this tract was once a naval proving ground, where some of the biggest bullets ever made, naval artillery shells, were tested against massive blocks of concrete. Today, we deal here with some of the smallest bullets in the universe, with which atoms are smashed to release atomic energy. And releasing atomic, or more precisely, nuclear energy, is the prime business of this section of southeastern Idaho. Here, there are more reactors of more advanced and different types than in any equivalent anywhere. This rolling desert plain has been nicknamed Prototype Prairie, because here the experimental first models or prototypes of power-producing nuclear reactors are built and put through their paces. Our greatest test reactors are also located here, reactors in whose fierce atomic fires we test the very materials out of which we hope to build new and better reactors. Locate on a map the hundreds of reactors built, planned, or under construction in this country alone in recent years. Almost every one of them owes a heavy debt to the work at NRTS. Indeed, many could not have been built at all until that work was done. Because most of our knowledge is freely shared, these threads of obligation to the testing station also reach around the world to numerous foreign countries where new reactors are profiting from our experience. The reactor testing station has deep importance, not only to builders of reactors, but to countless millions of people who never heard of the place, who may never even see a reactor, let alone build one. This importance stems from a shortage that is not present today, but may be closer than is generally realized. A shortage of energy, of power. Almost every tangible aspect of our civilization is based on a tremendous consumption of cheap power, chiefly supplied by the burning of our fossil fuels, coal, natural gas, and petroleum. We are now finding out that our world simply does not contain enough of these fossil fuels to allow us to go on spending them at our constantly increasing rate for any great time in the future. This bleak prospect has been altered by the advent of nuclear energy, which is already helping meet the world's sharply rising demands for power. Also, nuclear power plants generate their energy without adding to air pollution. But more important, they conserve more of our irreplaceable fossil fuels for making steel, plastics, medicines, gasoline. These, then, are some of the compelling reasons why so many experimental reactors of so many different types are being built in this Idaho testing area. Our nation's hopes for the development of tomorrow's power are centered in these reactors, silent furnaces that burn a cold, shiny metal, uranium. Today, most people find no strangeness in our concept that all matter is made up of atoms. Natural uranium is a mixture of two kinds of metallic atoms, uranium-238 and uranium-235. Most of these atoms are relatively stable uranium-238, or more simply, U-238. Only one of every 140 natural uranium atoms is the richer, more excitable U-235. Both metals look exactly the same. In fact, they can't be separated chemically. Now, if one of the tiny speeding particles that we call neutrons happens to collide with an atom of U-238, it may simply bounce off, or it may be captured and thus absorbed into the atom. If, on the other hand, the neutron happens to hit a U-235 atom, it may split or fission the atom into several fragments. Part of the fissioning atom changes from matter into energy, most of it appearing as heat and penetrating radiation. In this release of energy, atomic power is born. The leftover pieces of the broken atom are called fission products. They are intensely radioactive and are now entirely different elements of lighter weight, no longer uranium of any kind. A very important part of the fission process is that the breaking atom throws out 2 or 3 of its own neutrons, each one of which may in turn hit and fission still another atom of U-235. Thus, we may obtain a constantly increasing number of fissions, a chain reaction, the reactor people call it. And that brings us to reactors. In a reactor, we try to keep a chain reaction going at an even, rather than increasing, rate to give us a steady and controlled release of power. We can illustrate the basic reactor concept by starting with a simplified version of a reactor core. This may consist of a number of plates or rods of uranium metal called fuel elements, possibly enriched by addition of an extra percentage of the fissionable U-235, both for compactness and so that it will be easier to start and maintain a chain reaction. The core will be located inside of a tank or reactor vessel, and outside of it, we will want a heavy shield of metal or concrete to protect working personnel from radiation. Next, we will fill up the spaces between the uranium plates with water, graphite, paraffin, or any other material that will do a job that we call moderating. This moderator slows down the swiftly traveling neutrons to speeds at which they have the best chance of causing new fissions, rather than being captured by the U-238 atoms or bouncing off and finally escaping entirely. We selected water for the moderator in this simplified example because it also does such a good job as a coolant, transferring or carrying away the heat of the fissioning atoms. Now, with the water in place and the fuel elements correctly positioned, the reactor is ready. In fact, it would produce energy much faster than we wish, except for one thing. We also insert in the core a number of control rods. These are normally filled with some material like cadmium or boron that will quickly absorb many of the increasing numbers of neutrons and subdue the fission chain reaction. As soon as we begin to pull the control rods out of the core, the rate of fissioning will again increase up to the level determined by the given rod adjustment. When the control rods hold the fission rate at just the right level, the reactor is critical, with a controlled and sustained chain reaction. The steady release of heat makes the moderating water boil and give off steam. If we now cap the top of our reactor tank, we have a working steam boiler. We refer to this type of arrangement as a boiling water reactor. We can now pipe the steam off to drive a steam turbine and electrical generator, and we have a full-fledged electric power plant. A variation on this design is called a pressurized water reactor. In this, the cooling and moderating water is kept under high pressure so that it will not boil and turn into steam, even though it gets extremely hot. Circulating through a closed circuit, this water passes through a heat exchanger, which transfers heat to a completely separate second flow of water. Inside this second stage, the heat does produce steam to drive a turbine and generator. In some reactors, the moderator may be a solid, like graphite, and the coolant may be a substance other than water. Sometimes gas or even molten metal are circulated through the core to carry the heat to the heat exchanger. A great many variations are possible, but almost all power reactors in Idaho or anywhere else use basically the same simple principles. However, the theoretical and engineering jobs that translate these principles into useful power are tremendously complex. Take, for instance, the uranium fuel elements of the reactors. Perhaps the fuel is used in the form of slim, plated, perfectly machined and polished rods. Perhaps the fuel is sandwiched between sheets of protective metal called cladding, then rolled out thin, and finally cut and welded into a precisely dimensioned rectangular grid, or some other machinist's nightmare. How enriched should the uranium be for best results? Shall the protective cladding be of aluminum, zirconium, stainless steel, or what? Sometimes the fuel does not consist of metallic uranium at all, but of a ceramic form, such as uranium oxide, again possibly in metal-clad plates, rods, or even small pellets, and so on. It is possible to wring scores of changes on this solid fuel question alone, but every good idea must be tested before being used. Similarly, the coolants must be tested, the moderators, the heat exchange methods and materials, and 1,001 other items. First as experiments in test reactors, and later as part of reactor prototypes themselves. These are the jobs that get done at NRTS, where the proof of the pudding is in the successful functioning of the reactors. But the NRTS is not all reactors. Over in the central facilities area of the station, the Atomic Energy Commission maintains a number of services in support of the various nuclear facilities. Many of these facilities and all of the reactors are operated for the government by private contractors. These contractors include some important names in American industry, working here in partnership with the American government to learn the secrets of tomorrow's power at this unique engineering laboratory in the desert. The isolation out here gives us a chance for some large savings in developmental time and expense, since it permits us to do extremely valuable destructive testing. An early case in point was BORAX-I, the first of our experimental boiling water reactors. Tests to demonstrate the basic stability of this type of reactor were deliberately carried to extreme limits until the power surges produced experimentally became so large that they destroyed the reactor. We learned from these tests that such a blow-up could be made almost impossible in normal operation. Still, we would not have dared to conduct such deliberate terminal testing in a populated area. The findings of the first borax experiments were of great value in the design and testing of later reactors in the same family, lineal descendants, which build on and vastly extend the earlier knowledge. In the genealogy of experimental borax reactors, number 3 was unique in being the first to provide sufficient electricity from nuclear heat to illuminate the streets and homes of an entire American community. BORAX-IV, in the same building, gave us valuable new data on conversion of thorium to fissionable uranium. Still later, BORAX-V was designed to investigate the production of superheated steam by recirculating the moist steam produced by one set of fuel elements in the core through a second set of elements in the same core. The resulting drier, hotter steam, almost 900 degrees Fahrenheit, is comparable to temperatures produced in the most efficient conventional power plants. The BORAX-V experiments have been important steps toward lower cost power from the atom. An important outgrowth of the early borax experiments is another family line of reactors known as SPERT, or Special Power Excursion Reactor Tests. A major portion of the Commission's intensive program of reactor safety investigations is carried out here. The aim is to develop knowledge of reactor behavior so that nuclear power plants can be designed for greater safety, operational flexibility, and less cost. By pushing the SPERT reactors to extreme limits, their ultimate self-shutdown mechanisms can be studied under a wide range of conditions and with many different cores. The open vessel SPERT-I has been deliberately pushed to extreme limits, and on November 5, 1962, a highly enriched plate-type core was completely destroyed. Yet in subsequent tests, a low-enriched uranium oxide core successfully withstood even greater power bursts, a development of major safety significance to the general public because the same kind of fuel is used in large nuclear power stations. SPERT-II can be operated as a closed and pressurized system at raised temperatures and using a variety of moderators, including heavy water. SPERT-III is considered the most versatile facility yet developed for studying high-power reactor safety. It provides for operation at high power levels and with different cores, with slow or very fast coolant flows, water temperatures up to 650 degrees Fahrenheit, and pressures up to 2,500 pounds per square inch. The youngster of the SPERT line is number 4. This is another open pool reactor with greatly improved facilities for exploring power fluctuation problems beyond the capabilities of SPERT-I. In addition to its larger coolant reservoir and resultant heat absorption capacity, larger cores can be examined in SPERT-IV. It should be realized that the knowledge generated at SPERT, as well as other NRTS facilities, has almost simultaneous impact on the outside world of both American and foreign industry. Data from our earliest NRTS studies have influenced the design of our most advanced boiling water reactors. Even as first-generation developments, these plants made significant contributions to lower-cost electricity from atomic heat. The concept of the pressurized water reactor, as distinct from the boiling type, has proceeded along two different routes, military and civilian. A notable achievement in the civilian direction is the Shippingport Atomic Power Station in Pennsylvania, the nation's first large-scale nuclear plant to generate electricity for civilian power grids. However, the important bulk of the Idaho prototype testing for reactors of this pressurized water category was military in its first application, aimed at freeing our naval vessels from their ancient need for either frequent returns to port for refueling or the alternative of potentially hazardous refueling at sea. In particular, submarines have always been handicapped by refueling needs and by the much more dangerous requirement of frequent surfacing to recharge batteries, even in active battle zones. The possibilities of a submarine with atomic engines to free itself from the Earth's atmosphere, thus giving it almost limitless range underwater, offered the promise of revolutionizing naval warfare. Picked construction crews built a full-scale submarine inside a well-guarded building at NRTS and installed a full-scale nuclear engine. The remarkable performance of this ship in the desert resulted in the world's first nuclear-powered ship, the famed submarine Nautilus, and the subsequent addition to the U.S. fleet of numerous atomic sister ships, many of which carry the mighty punch of Polaris missiles. Pressurized water reactors were also selected for the next big job of the station's naval facility, development of the land-based prototype of the engines which now power large naval surface ships, such as the missile cruiser Long Beach and the giant aircraft carrier Enterprise, which actually have to hold down their effortless speed to avoid running away from their non-nuclear escorting destroyers. A more recent prototype reactor under development in the Naval Reactors area at NRTS is the S5G, the Natural Circulation Reactor, which uses no pumps, but only natural convection to circulate its cooling water. Many of our military operations must be carried out in remote areas, which can be supplied with conventional fuel for heat and electric power only through great effort and expense, and sometimes at substantial risk. NRTS has been the home of a major part of the Army's mobile reactor development program, which of course is also of great interest to the other services for electric power production. A first stage in the approach to nuclear power plants that can be moved without disassembly was the GCRE, gas-cooled reactor experiment. GCRE's major claim to fame is that it was the proud parent of ML1, the Army's mobile low-power reactor plant number 1. This is the world's first direct and closed-cycle gas-cooled nuclear power system, and the first prototype of a truly mobile power reactor. The reactor and the turbogenerator systems weigh about 15 tons each and are mounted on separate skids. Both can be transported in a single airplane or by truck trailer, barge, ship, or sled. The much lighter transistorized control cab, also skid-mounted, can be carried on a 2.5-ton truck. The entire plant is designed to be moved 24 hours after shutdown and be operating again within 12 hours after arrival at a new location, turning out 300 to 500 kilowatts of electric power for almost 2 years on a single loading of nuclear fuel. A few miles farther west is another variation on the nuclear power plant theme, the organic moderated reactor experiment, now retired from active duty. OMRE's experimental work is now completed, but some of its family traits have been inherited by organic cooled reactors at several sites in Europe, Canada, and in the United States. Another important family of reactors at the station is found in the test reactors area. The primary purpose here is to find out in weeks or months what would otherwise take years to discover in normal reactor operation. The oldest, in a sense the granddaddy of the family, is the MTR, the Materials Testing Reactor, a name that has become famous in scientific circles during its tens of thousands of operating hours. Every reactor built or being built in the world today is directly or indirectly indebted to the MTR. Through or to regions closely surrounding the core of this water-cooled reactor go 2 kinds of pipes. These loops and irradiation holes make it possible to insert sample substances for exposure to intense gamma rays and a tremendous flux of more than 100 million bombarding neutrons per second over every square inch. These tests are extremely important because of the sometimes weird and unexpected things that heat and nuclear radiation can do to reactor construction materials. Most particularly, we must know how fuel materials and their alloys behave. Some samples bow or twist or bulge in ways that might lead to cladding ruptures and escapes of radioactivity. Such things must be known before the materials go into our military and civilian nuclear plants, or we risk dangerous and extremely expensive mistakes. The MTR's primary role of testing has been augmented by extensive research and development work in neutron physics. For such purposes, as illustrated in this top view, we use beam holes through the heavy shielding to tap the reactor's reservoir of neutrons and channel them through a variety of measuring devices. One measuring device is the neutron crystal spectrometer. It can bend and in this way select out of a wide range neutrons of any given speed that we want to work with. 2 other instruments working at beam holes use very fast rotating shutters and time of flight methods to sort out and measure the different neutron energies during millionth of a second pulses. Comparing the number of neutrons before and after their beam bombards a sample material tells us how hungry that material is for neutrons of each energy. Knowing the neutron appetites enables reactor designers to predict how desirable this or that material will be as a reactor component. The MTR is also world-renowned for its production of custom-tailored radioisotopes. Common elements, ordinarily not radioactive, are changed and given remarkable properties by exposure to the MTR's high neutron flux. For example, cobalt-59 becomes radioactive cobalt-60, hundreds of times more potent than radium for cancer therapy. Orders from all over the world are filled, such as irradiation of an iron bolt for a laboratory in Japan, or high specific activity calcium for a Swedish hospital. Nearby is an integral part of the test reactor program called the Advanced Reactivity Measurement Facility. Here, 2 low-power reactors measure changes in the nuclear properties of material samples before and after irradiation, a chore they perform with unequaled sensitivity. The ARMF is another vitally needed approach to improved reactor design. It can tell us in a matter of minutes, and with only a tiny sample, whether millions of dollars worth of a potential atomic fuel will do the job expected. Obviously a huge economy. South of the MTR is the Engineering Test Reactor, or ETR, which grew out of the overwhelming demands on its predecessor. This newer giant, with 175 million watts of heat output to the MTR's 40 million, and with loops that go right through the core, can handle much bigger samples than the MTR, and at higher temperatures, higher pressures, and with a much higher neutron flux. Northwest of the MTR is the newest, most advanced, and largest of the 3 major test reactors, appropriately named ATR, for Advanced Test Reactor. Construction of the ATR was started in late 1961 and held to a tight schedule because of the urgent need for accumulating data more rapidly to keep pace with fast-moving reactor technology. The ATR has a heat energy output of 250 million watts, nearly half again as much as that of the ETR. Its ingenious core design permits multiple, yet simultaneous, irradiations under a wide choice of conditions. The ATR core contains 9 loop spaces, which can take long vertical pipes as large as 5 inches in diameter. These can hold solid specimens up to 4 feet long, and each pipe can be made a completely closed test loop with its own pumps, heaters, or what have you, to circulate liquids, gases, or slurries, pressurized and hot, or the reverse. Looking down at the 9 pipes, we see the truly unique feature of ATR, the cloverleaf arrangement of the fuel elements. The power levels in different regions of this serpentine core can be adjusted to provide different neutron fluxes for individual loops, a time and money-saving flexibility that could otherwise be accomplished only by 9 separate reactors operating at a combined power level 3 times greater and therefore much costlier than the ATR. The MTR, ETR, and ATR are huge and expensive machines, but without them, reactor design would still be limping blindly in its earlier phases. No one today can foresee a time when these remarkable tools will stop paying again and again for their original cost. Strangely enough, at first thought, a much smaller test unit in another area can produce a substantially greater neutron flux than any of the 3 giant test reactors, but only for very short intervals. However, the rate at which the flux increases is so rapid that very important tests can be performed in the Transient Reactor Test Facility, or TREAT, as it's commonly called. By limiting its high power output to very brief transient pulses, this vast reactor fuel and safety test facility can safely flood its experimental spaces with enormous concentrations of neutrons. Test materials in the spaces can thus be subjected to fluxes and heats far higher and more destructive than they are ever expected to receive in actual service. And the way in which test fuel elements, for example, fail, if they do fail, tells us how we can improve reactor design. High-speed cameras look inside the reactor to record results when the neutron barrage causes a sample fuel element to react so violently that its cladding ruptures. Vaporized sodium bonding material and molten uranium fuel spurt out of the open seam when failure occurs. "20 miles north is TAN, a complex called Test Area North. This was originally the site of ANP, where significant progress toward development of a nuclear airplane was made in the 1950s. Since that project was discontinued in 1961, several other programs have been assigned to the area. The hub of activities in this area is the Technical Services Facility, or TSF. Here are several large shops. The cold shop handles hardware assembly jobs involving no radioactivity. The warm shop receives slightly radioactive assemblies for servicing, adjustment, or modification. And for intensely radioactive materials, there is a mammoth hot shop equipped with remote handling devices of several types, some for delicate and precise work, and others massive enough for industrial-sized operations. The service shops and other existing facilities in which testing is carried out are being shared to great advantage by new programs assigned to Test Area North. The testing facilities are situated in a fan-shaped pattern around the services area. Best known is the Initial Engineering Test Facility. A 4-track railroad connects it with the service shops, thus permitting reactor experiments to be shuttled back and forth on double-width flat cars for testing and post-test analysis. This unique feature has made the IET a valuable adjunct to safety testing. A case in point was the testing of a SNAP 10A auxiliary power space reactor in April 1964. The results showed that such a device would immediately destroy itself instead of building up a high inventory of radioactive fission products should it fall into water. Tests like this are part of STEP, the Safety Test Engineering Program, which involves engineering scale field testing to demonstrate the safety of aerospace and land-based reactor systems. Another STEP testing complex, 2 miles to the west, is the Field Engineering Test Facility. Scheduled for operation here is the loss of fluid test, called LOFT, which is designed to investigate the worst accident that conceivably could happen to a water-cooled reactor. Also in Test Area North is the 710 Research Reactor Experiment, studying the use in reactor design of refractory metals such as tungsten and tantalum. These metals can maintain high strength even when extremely hot, but are metallurgically very difficult to fabricate. Hence, a large study effort is required to make use of their virtues. Next door to 710 is EBOR, the Experimental Beryllium Oxide Reactor Facility. This helium gas-cooled experiment is a promising concept for low-cost electricity and process heat. Near the center of the NRTS is a support facility of importance to the entire station. This is the ICPP, or Chem plant, the site's biggest single plant investment and a final destination of burned out or expended fuel elements removed from reactors throughout the free world. These spent elements are not burned out in the sense that a stick of wood burns out in a fire. There is no complete utilization of the fuel. Even after a reactor core has operated for hundreds of hours, only a matter of ounces of uranium will have been fissioned, perhaps less than a quarter of the load. By then, however, the fragments of shattered atoms that we call fission products will be soaking up so many of the bombarding neutrons that a chain reaction cannot continue. The core is effectively poisoned. Then the fuel must go into the chem plant for processing to dispose of the poisons and salvage the unused uranium for new fuel elements. Through an engineering triumph called the continuous dissolution process, spent elements can now be fed into the plant stream as fast as desired, without interrupting the processing cycle. 99.9% of the precious unburned U-235, worth $300 an ounce, is recovered for reuse. Samples of the plant stream can be drawn off at various stages for analysis in thick-windowed hot cells. Still, other cells have facilities for separation of very valuable radioactive elements, such as iodine-131 and cesium-137, from the fission product soup of the mainstream. The plant has been jokingly described as a multi-million-dollar garbage disposal for reactors, but this tremendous and vital job is no joke. For every 1 pound of uranium-235 recovered, the plant ends up with 1,000 pounds of liquid wastes. What can you do with a steady output of thousands of gallons of radioactive and corrosive liquids that you can't throw out or even allow to leak out for the next several hundred years? We have been safely storing these wastes in very expensive stainless steel underground tanks surrounded by concrete vaults. But this is not a very practical long-term solution to this difficult problem, particularly since these tanks cannot be considered permanently leak-proof. One of the most encouraging advances to date is demonstrated in successful operation of the Waste Calcining Facility, or WCF, the world's first unit for plant-scale conversion of highly radioactive liquid wastes to solid form. In the WCF process, the waste solution is sprayed into a heated bed of solid particles, fluidized by blasts of air, leaving a calcined residue of small, dry granules that takes up only 1/10 as much space. A continuous airstream blows the excess granules through underground tubes and into buried storage bins of less costly construction than liquid storage tanks. The stored granules won't seep or leak and are non-corrosive. Every 200 days the plant operates, it calcines the contents of a $1 million liquid storage tank. Less costly management of liquid wastes is one of the problems that must be solved before we can obtain economic nuclear power in all areas. And it is just one of the research jobs of the huge engineering laboratory that we call the National Reactor Testing Station. The last 2 reactors on our rounds are quite different in many respects from the others we've seen, and totally different in one momentous way. They can breed more new fuel than they consume, a phenomenon of obvious importance to the long-term future of atomic energy. The pioneer in the new direction was EBR-I, Experimental Breeder Reactor number 1, the world's first reactor to demonstrate the breeding principle and to produce useful amounts of electricity. A follow-on reactor of the same family is Experimental Breeder Reactor number 2, a key facility in the AEC's program for meeting long-range energy needs. Like its predecessor, EBR-II is a fast reactor. That is, it contains no moderating material. The nuclear fissions in its fuel are caused by neutrons traveling about 13,000 miles per second, compared to 1 mile per second when slowed down by passage through a moderator, such as graphite or water. Using non-moderating liquid metal to carry heat to its steam-generating plants, EBR-II operates at high temperature for efficient power production and low pressure for safer and potentially more economic operation. However, the main distinction is that EBR-II can manufacture more fuel than it burns. You'll remember that when a neutron hits an atom of U-235, it will probably fission it. If a neutron hits a U-238 atom, it will most likely bounce off or be absorbed without causing fission. If the neutron is absorbed, it is not wasted because the U-238 atom that swallows it turns into neptunium and then into plutonium, plutonium-239, a fine reactor fuel in its own right and superior to U-235 in fast breeder reactors. The significance of fast reactors in this connection is that their high-speed neutrons produce more new neutrons per reaction than we get out of reactions caused by the slow neutrons in our moderated reactors. Therefore, the fast reactors have more spare neutrons than the moderated reactors to apply to the job of breeding new plutonium fuel from the relatively inert U-238. Also, fewer of these spare neutrons are wasted by absorption into structural materials. When the EBR-I first tested our theories about the breeding of plutonium in 1952, its fuel elements were surrounded by a breeding blanket of natural uranium. After a period of reactor operation, the breeding blanket was analyzed, and it was confirmed that for every atom of U-235 consumed, a little more than one new atom of plutonium had been created. Plutonium which could be extracted from the breeding blanket and used in new fuel elements in the place of U-235. This was the result that told us we can burn substantially all of the uranium we can find instead of just 0.7% if we learn to build the right kind of reactors. Otherwise, as soon as we burn up the tiny fraction of U-235 in our natural uranium, we would end up with mountains of U-238 that we could never burn, totally useless for power. By perfecting the fuel breeding process, however, we make available an almost inexhaustible supply of energy, more than 2,000 times the energy contained in all our remaining fossil fuels. The benefits of fuel breeding go still further. They promise us power from supplies of the element thorium. When an atom of this metal in the breeding blanket of a reactor absorbs a neutron, it is transmuted into unstable thorium-233. It then decays to protactinium-233 and then to uranium-233. Like plutonium, this new element uranium-233 is fissionable and another potentially good nuclear fuel. The engineering problems that must be solved before our reactors are completely effective for both breeding and power production are complex, enormous. It may take decades, but success will be rewarding beyond measure. Reactors able to breed new fuel as they burn the old, while turning out their enormous floods of power, could supply our major energy needs for centuries to come. We could both have our cake and eat it. EBR-II's job is to develop plutonium fuels for use in future power reactors and to advance the fast breeder technology in general. Integral to the operation of EBR-II is the fuel cycle facility. First plant-scale attempt to melt, refine, and refabricate discharged fuel elements on the spot, all by remote control. Pilot techniques have demonstrated how EBR-II spent fuel elements can be extracted from the reactor core, melted down and purified, then recast into completely new fuel pins, entirely by remote processes operating behind thick shielding windows. This integrated pyrometallurgical processing could reduce capital costs by eliminating delays of up to 6 months occasioned by conventional processing and refabrication. It is one more complex but important step in the assignment that keeps NRTS so endlessly busy. The mandate to develop and test practical sources of the atomic power needed to keep our civilization healthy and its future secure. Not enough power for all time, nor for all needs, but a bridge to the day when we can tame the energy of the sun by mastering the thermonuclear sources of its fire in fusion reactors. And their prototypes may first appear right here at the National Reactor Testing Station in Idaho, where so many earlier plants have grown from theory to demonstration. This is the home of the new power, the power of tomorrow.